All right. Okay, I don't know what's happening. Well, hopefully people start showing up. I think it's just me. Um, so yeah, hope that everyone who is here is doing well. I don't know. Oh hey, hello. How's it going, Tommy? Um, I guess we'll this is not the most efficient way of communicating. But that being said, I appreciate you coming to the stream, and I hope that you enjoy what I have in store for today. So yeah. It says I have 3 viewers. That's awesome. So I think that means, say what I said again. Oh, I just asked how you were doing. And then I made like a comment about how it's difficult to communicate using this method, just because like there's a delay. See, it's funny because I was thinking of what to say, so there was a delay in me being able to finish the sentence, as well as like the actual delay between. This is so dumb. The actual delay between the YouTube and the other stuff. So yeah. Anyways. Well, I say hi to Charlie. I invite him to watch. You know, as per usual. And I hope he's doing well. Hopefully, he's enjoying his tours and the big decision coming up. So. I'm gonna wait until 4:05 to begin. Charlie says he would watch, but it's too much work to get his phone out of his pocket. Oh, but his finger's hurting. Okay, I mean that's fair. Are you guys like in the same room? Because then you could both like watch me at the same time, and I think that would be okay. Yeah. Oh, that's cool. Where are you guys going? How is the stream quality in the car? Oh my God, his finger's bleeding. Oh boy, that does not sound great. Do you have a Band-Aid or anything you can wrap it up with? Yes, ouch. I agree with that sentiment. Yeah, well, wow. I hope that situation turns out to be okay. Oh, okay. That is good to hear. See, so I have it on the stream on my computer, and I also have it on my phone to so I can see the comments. And so on my computer, it's bad. Uh, But on my phone it's better. So it might just be my computer. Anyways, it looks like that it's about oh, can everyone in the car hear me? That's awesome. I mean, it's not awesome that like Charlie's finger's bleeding. Anyways, I say hi to everyone. Anyways, it's 4:05, so I think it is about time for me to begin. So hello everyone. My name is Mark. This is my channel, Mark Does Math, where I do math and other math-related things. So, as per usual, the format I've been going with is I'm spending kind of the first half explaining a kind of concept, or in this case, I'll be doing a specific problem. And for the kind of second half, I'm going to kind of open this up to questions from the chat, anyone who's interested, who has a math question, or just wants to talk. I made it work last time with Discord and cool stuff like that. But without further ado, I think that we should get started on the actual math problem that I want to go over. So hopefully I am still in a visible form here. But yeah. Here we have before I start, I haven't even said what the problem is. But I first kind of want to introduce the idea that we're going to be talking about. So first of all, we have this omega n, which is e to the 2 pi I over n. And then we have r sub n, which is a matrix, where the top left entry is omega n, the bottom left is 0, the top right is 1, and the bottom right is also 1. You might be looking at this and thinking, gee, Mark, what is e, and what does it mean to raise it to the 2 pi I over n? And for the most part, I'd say not to worry about it. Except for the fact that I, right here, I'll circle this, is the imaginary unit. So in the sense that I squared is equal to -1. And so e is a real number raised to an imaginary number. Okay, so that's the concept. But what is the question? What do we want to find out? So what we're looking for is we want to know, does there exist a k in the natural numbers such that r sub n raised to the k is equal to the identity matrix, which is 1, 0, 0, 1. And what's cool about the identity matrix is that the identity matrix multiplied, it's like multiplying by 1 if you multiply a matrix by an identity matrix. And so the identity property of multiplication, which is generally saying like that a times 1 is equal to 1 times a, which is equal to a. That's kind of the identity property of 1. And so in matrix form, this matrix has the same property. Okay, so we want to know, does there exist a k such that we can raise this matrix to the power k, and it equals the identity? And, because there's always an and what is the smallest such k? If it exists. So I'll just write, what is smallest k? So let's see what's going on here. First of all, we want to figure out what is r sub n to the k. So we can figure this out by thinking, what is r sub n squared? So r sub n squared is omega n 0, 1, 1 multiplied by itself, omega n 0, 1, 1. And I guess I'm going to assume that we know how matrix multiplication works. If there is any confusion, as always, any questions and stuff, you can ask in the chat. But I'm just going to go ahead and kind of perform the computation. So there's a computational rule. And so we can find the first column, right, by multiplying this column by the matrix. So the top left entry is omega n squared. Yep, and then the bottom left entry is 0. And then the top left entry, we see that these are 1s, so we can find, we can find the right column just by adding the vectors together, or adding these rows together, essentially. So we have omega n plus 1, and we have 1, right? Because 1 times 0 is 0, or 0 plus 1 is 1. And we have 1 viewer. I think that might just be my phone, but that's okay. So we have this, and what I want to wonder is maybe we can kind of generalize. Do we see a pattern? And we could keep going, but I have an idea. So I'll write it down here. Idea. And let's kind of move this up. R sub n to the k is equal to a matrix, obviously. So we have omega sub n to the k, 0. The sum as j goes from 0 to k minus 1. Right, so if k is 2, then j goes from 0 to 2 minus 1, so from 0 to 1, inclusive. And this is of omega n to the j. And this last entry here is 1. So hopefully this makes sense. I want to see if I can select it. Well, let me... Can I just drag it down? Yeah, there we go. There we go. So this is my idea. Now, how can we prove this? Well, we can use something called induction. So that is, we assume a base case, and then we assume that if it works for one case, it works for the next case. So yeah, let's just say base case is k equals 1. And so that means that r sub n to the k is equal to Rn, which is omega n 0, 1, 1, which is omega n to the 1. 0, 1. And then this here is the sum as j goes from 0 to k minus 1. So k minus 1, well, k is 1, so 1 minus 1 is 0. So it goes from j equals 0 to 0. I know this looks kind of weird. Wn raised to the j. And thus we have proven the base case, right? Because 1 is just something raised to the 0. And so when these two are the same, we just have one term. So that's very nice. Yeah. So now we want to show the inductive hypothesis, or the induction hypothesis. So we assume the above is true for some k. And now what we want to do is we want to look at r sub n raised to the k plus 1, which is r sub n to the k times r sub n, which is, now remember, right, we're assuming that this property holds true for k. So we have omega sub n raised to the k, right, over, not over, here we have 0, here we have 1, and here we have a sum from j equals 0 to k minus 1, hopefully it's clear that's a k, of omega sub n to the j. But we're not done, right? Because we have to write this matrix, r sub n, which is omega n, 0, 1, 1. Okay, let me zoom out because so I have some more space to write it. So we have this. So now we can use matrix multiplication again. So we get omega n to the k plus 1, 0. Wait. Yeah, because we ignore the right column, yeah. And then to find the second column, we just add the rows together because they're both 1s. So we have omega to the k plus this sum, j equals 0 to k minus 1 of omega n to the j. And then to add the last two, well, we add these together, so 0 plus 1 is 1. And we can see that we can combine this infinite series together, right, because we just change this. In fact, I'll just do this right here. We can just change this to a k, right? And it turns out that's the same. I don't know why it's not erasing. I want this because I don't want this to be a negative, because that's like the opposite of it just is not, it's not working. That works. Okay, I guess it's going to be a positive. Yeah, it that's gonna be a positive sign. I'm sorry, I don't know how this is working. So okay, so we have proved our idea, right? Our general idea for a formula for Rn raised to the k. So you might be looking at this and seeing, well, what does this infinite sum resemble? And we see that it actually resembles a geometric series, right? And what is the formula for the first n terms of the geometric series, or the first n, the partial sum of the geometric sequence, right? Well, we learned that in the formula last time, so let's kind of generalize this. So Rn to the k is omega n raised to the k times, now the first n terms, right? So we have our initial term, which is, well, 1, and then we subtract the last term, which is omega n to the k minus 1. And then we have 0, and then we, oh wait, no, in the denominator, and then we have 1 minus omega n right there, and then we have 1. Right, and that comes from my last episode, so last week, when we showed, right, that kind of additive step. So yeah, okay, but we want to figure out what is the smallest k such that this is true. And so now, I provide a new idea, in green, and this idea is this. K is equal to n. That's right, the same n that r sub n raised to the k happens to be. So what is r sub n raised to the k? Well, we can see what it is. So we have omega n, or this shouldn't be k, I mean, we know k is n, so let me write n. So we have omega n raised to the n, 0, this is a 1, and then you have kind of a wonky fraction, right? We have 1 minus omega n to the n minus 1. And then the denominator, we have 1 minus omega n. Because I'm pretty sure, you know what, we'll see where this goes, and then we'll see if I made a mistake. I don't think, we have a smaller audience today, so I think it'll be okay if I make a mistake, we have to backtrack. Okay, because what is omega n, right? If we go all the way back to the very beginning, omega n is e to the 2 pi I over n, right? So that means that r sub n raised to the n is equal to e to the 2 pi I over n raised to the n, 0, 1 minus e to the 2 pi I over n raised to the n minus 1, and 1. Which is, this is so much. But we keep going. Right, the first entry here is e to the 2 pi I n over n. And so the n's cancel out. And we get e to the 2 pi I, which we'll figure that out later. And then here we have 1 minus so we have e to the 2 pi I n minus 2 pi I, right? Yeah, it sounds about right. Over n. And then divided by 1 minus omega sub n. And then of course this bottom row we have 0, 1. Okay, what is e to the 2 pi I? Well, you're probably familiar with the notion. Oh my goodness. So let's say we have theta, and this has a length of 1. E to the I times theta is equal to this kind of, it's really equal to this point right here, if this is the real plane and this is like the imaginary plane. So in theta is the angle, right, between this line right here and the real axis. Oh my goodness. So if theta is 2 pi, well, that's the same thing as theta being 0. So really this is just the point where it's flat and it has a length 1. So it's just the real number 1. So you can put that here. The first entry is 1. Now, what's this entry right here? We have 1 minus e to the 2 pi I minus 2 pi I over n. So we can kind of, using the kind of exponential property, we can use a multiplicative property here. So e to the 2 pi I times e to the negative 2 pi I over n divided by 1 minus omega n. I think I might have done something wrong, which is not great. And then 0, 1. Let's see. Let us see. So, e to the 2 pi I, as we showed, this is just 1. So really we can just kind of erase this. E to the negative 2 pi I over n is not necessarily, I believe, I wonder if this formula here is wrong. This should be Wn raised to the k. Yeah, I think it should be. Yeah. Okay. Okay, actually, okay, I made a mistake. There wasn't supposed to be a minus 1, it was supposed to be raised to the k, which means we were going to get 1 minus 1. So really this is just 0, because 1 minus 1 is 0. So this whole entry is 0. So this matrix is equal to 1, 0, 0, 1. So there does exist an n, right? But the n is, I mean, there does exist a k. We know it equals n. But are we sure that n is the smallest integer? And so let's take a look here, right? This should actually be omega to the k, right? And maybe I'll kind of put this idea in different color. We have 1 minus e to the 2 pi I over n times k over 1 minus e to the 2 pi I over n. Right? We want this to be equal to 0, right? For it to hold. So we multiply, right? Because we're trying to see, like, could there possibly be a k less than n that this works? So this step implies, right, we can multiply on both sides, which means, and then, so let's say we multiply, well, I'm just going to skip some steps. This would imply that 1 is equal to e to the 2 pi I k over n. Okay, but remember, if e to the something I is like the angle, right, what would the angle have to be for it to equal 1? well, it would have to be like the angle would have to be a multiple of 2 pi, right? So this implies that 2 pi k over n is equal to 2 pi a, right? And thus we can cross stuff out like the 2 pi. And that gives us k over n is equal to a. But remember, if k is supposed to be a positive number less than n, it couldn't equal a, right? Which means that the smallest positive integer is n. So k is equal to n, which is what we wanted to show. Hello, Adam. Welcome to the chat. All right. So that was the problem that I wanted to show. Oh, and I did not want to upload files. That was kind of the cool matrix problem. It's cool because it uses the geometric series, and it uses complex numbers, and it uses matrices. So yeah, there was a lot. Yeah, and that was kind of the main thing that I wanted to show for today. So yeah. I don't know if I don't know how many people are watching or are interested, but I guess I'll open it up to questions if people are interested in that. Does anyone have any questions? I'll try to connect Discord. Give me a second while I set that up. So yeah, let me make a post in Discord. And then let me make a post in okay. Oh, that's funny. I just saw my own message show up in the chat. Oh, it looks like my stream is lagging. No, okay, it seems fine. Okay, is it gonna let me enter the voice channel? Oh, everything is just lagging today. Anyways, I'm now on Discord, so yeah, if you have any questions, I'll probably stay on. I don't know. We have a smaller crowd today, so I probably won't stay after 5. So yeah, I hope everyone is doing well. I hope that, it's Friday. I hope people are looking forward to the weekend. I hope those of you who have classes that's all going fine. I know it's around like midterm season for quarter system people, so you might have just had a midterm or you're studying. Yeah, all that fun stuff. Lots of good stuff to think about. Yeah. So, anyways, I'll just be here. It looks like we have 3 viewers. That's awesome. I think that's more than we've had in a while. So that's very cool. Yeah. Uh, so, anyways, if not, I'll just chill here. I have you know, I always have stuff that I can be doing. I have stuff that I can be explaining. Um, so yeah. How is chat doing? I don't know. It looks like we have 3 viewers now. So that's cool stuff. Chat is doing okay. That's what we like to hear. That's what we like to hear, guys. I'm glad. Is it just okay, or is it like more? Is it like a good okay, or is it like a bad okay? Um, I guess I'm not gonna. Oh no, there's a delay, so it's gonna take a while, anyways. Okay, I'm gonna wait until like 4:45, and then I think I'll end the stream, which is okay. We had a slower day today, which is totally fine. I just had a quicker problem that I wanted to go over. Next week will be a little more of an involved calculation. But yeah, I am grateful to everyone who's been able to join the stream. Um, that stuff is always appreciated. It's always cool to share math and to work on math problems together. So yeah. Um, but yeah, anyways, I will be here for at least 7 more minutes. So it is never too late to ask any questions or voice any concerns. If you haven't, make sure to like this video and well, this is like a stream, but I think you can like a stream, and subscribe and hit the bell and all that stuff. Because it's important if you wanna get notified about future live streams and future things that I'm doing. I'm currently trying to get to 100 subscribers. So yeah. And with just a reminder, we have until 4:45. Of course, if there's any interest, I might go longer, but I think that I'm just working on stuff in the meantime. So yeah. Again, hope everyone's doing well. Hope you enjoyed the stream. So yeah, glad that very good. Okay, that's good to hear. Um, all right. Thanks for watching, everyone. Have a good rest of the day and have a good weekend.